Welcome to Stewart Observatory for our final lecture of spring 2026 in the Stewart Observatory Public Viewing Lecture Series, a series started in September of 1922 by Dean Andrew Ellicott Douglas. The bad news: it's cloudy. Therefore, the 21-inch radially wide telescope will not be open this evening for viewing at the conclusion of tonight's lecture. This is our last lecture of the semester, so I can tell you we will start again in September after Labor Day. And sometime over the summer, I will have, hopefully by August 1st, an entire schedule of what the lecture will be for the fall of 2026. So, we would like now to welcome from the Department of Journalism here at the University of Arizona, James Lockridge. Jim, please talk. Jim grew up in Hawaii, received his bachelor's degree in history from the University of Vermont. Yeah, I know. It wasn't just administration that our new president brought over from Vermont. And he is currently in the master's degree program in journalism with a specialty in science journalism. And the subject matter for tonight's presentation is part of his work on his master's degree in journalism. So without further ado, I ask James Lockridge to give us a talk on Standing on the Sky, a visual history of the Kitt rocket program. Jim.
Thank you. I feel the same way about this subject. I'm used to standing on a mountaintop, pointing at telescopes and yelling about them for 50 people at a time. So you get to watch me squirm and try to jam into a microphone tonight. I'll do. Forgive me if I get obnoxious, and I will be bold in my effort. So let's see. Forgive me for getting this going here. I'm going to reclaim my cursor. For us to talk about the rocket astronomy program of Kitt Peak, we have to have some context. Our story begins late in 1955. The National Science Foundation has just funded a search to find a location for a new national observatory. An observatory where astronomers could take turns using modern instruments and have shared access that wasn't bottlenecked by private institutions. Their first stop was above the clouds. They viewed photos taken by a Viking 12 rocket looking down on the southwest. And that view from space helped them narrow the choices of the mountaintops. And then astronomer Helmut Abt flew over 32 of them in the Cessna on the right, taking notes and photos. Those Cessna flights focused the potential sites down to about a dozen, and a crew led by Aidan Meinel began trekking up to their summits on horses and jeeps to learn how the seeing was. Dr. Meinel was a world-class optical instrument builder. At the time, he was hired to lead the site survey. He was associate director of Yerkes and McDonald's observatories. He was called a first-class instrument man and a very active, aggressive type. The largest telescope in the world then had a mere 200 inches wide. Meinel was conceptualizing one that was 500 inches wide. He couldn't help but think big. He was a project guy. At 5 of the best mountaintops, they set up 16-inch telescopes with electronic light meters, photoelectric photometers, built by Meinel to measure the transparency of the atmosphere. And they eventually chose Kitt Peak as the perfect site for the observatory. You'll see here on this official 1893 map that it's spelled Kitt's Peak with one T. And that's because an Englishman named George Rosecrooge was the Pima County surveyor at the time, and he named Kitt Peak for his sister. Kitt, with two T's, was her married name. The name on the map was changed from one T to two T's in 1930 by the U.S. Board on Geographic Names to match the family name, thanks to the wife of the son of his sister. Will not be tested. The original name of Kitt Peak is Yolgum Duak, which translates into Red Stick Mountain. The red sticks are the branches of the manzanita bush, which has a lovely maroon bark and grows there. Kitt Peak original name was Yolgum Thuag because it is a sacred mountain of the sovereign Tohono O'odham homeland. And permission to build an observatory had to be asked for. And this conversation took a couple of years, and it resulted in the lease of land on and around the mountain to the National Science Foundation. And you might wonder why we're bringing manzanita bushes and the Tohono O'odham into a story about rockets. And there's a reason. Kitt Peak, our national observatory, wouldn't exist without this ongoing intercultural collaboration. The astronomers of Kitt Peak honor the past, present, and future generations of the Tohono O'odham. The Tohono O'odham called the astronomers the men with the long eyes. Dr. Meinel became the National Observatory's first director.
And if I could just interject here.
Yes.
As a historical note, in 1955, when the National Science Foundation was in negotiations with the Tohono O'odham, the elders of the tribe were brought here to the Stewart Observatory 36-inch telescope, the original one that used to be in the stone, to look at Saturn. Yeah. I didn't know if you were going to mention that, but I have to say that.
There's so much exciting stuff. Oh my gosh, we have so not even started yet. We're setting the scene. And it's so true. So in 1958, America had established a national observatory. Eventually, the mountaintop would be covered with dozens of telescopes. But before a single major telescope was built, the National Observatory was creating a space division. To understand how we ended up with a rocket program, we have to know how we even had a space division in the first place. Remember how Dr. Meinel was a man of high energy. The monotony of construction and daily operation was rough on Meinel, who liked to pursue projects. The observatory's leadership, the board of the organization that we know as AURA, the Association of Universities for Research in Astronomy, let Meinel pursue his interest in space to prevent him from leaving for a job with Princeton's space program. And this is during the space race. The Soviet Union had escaped Earth's gravity with Luna 1, hit the moon with Luna 2, and photographed the dark side of the moon with Luna 3, all in 1959. It was an exciting and competitive era in the United States. And this is an image of the board of Aura and National Science Foundation representatives visiting the 36-inch telescope under construction at Kitt Peak in 1959. The first space division project was research that would lead to building a 5,000-pound space telescope with a 50-inch mirror. In 1959, Meinel and the board of Aura presented this proposal to the National Science Foundation. This is a model of the space telescope. In May of 1959, Meinel was visited by the Army Ballistic Missile Agency to discuss how the space telescope might be designed to be carried to orbit by a Saturn rocket. And this is a test space mirror in a frame. The second scientific paper issued by the National Observatory was titled Astronomical Observations from Space Vehicles. It was by Dr. Meinel. In July 1959, Nancy Grace Roman, NASA's first chief of astronomy, visited Kitt Peak and the Tucson Laboratory to talk about the space telescope. And in August, Meinel met with Werner von Braun and his staff to talk about the telescope. And together they watched the test of a Jupiter missile firing and saw a mock-up of a Saturn propulsion system. And this is the space mirror. The backside is reflected in another mirror. Kitt Peak was experimenting with metal mirrors that could be light enough to launch to orbit, especially aluminum mirrors covered in nickel. And the 28-inch test mirror is here in a shake frame. They were learning if it could withstand the vibration of a rocket launch. In 1965, a 430-pound, 50-inch aluminum mirror was installed in this purely remotely operated telescope. It was a test bed to learn how to operate a space telescope from Earth. Kitt Peak was inventing this technology. The mirror was a 1/4 inch thick at its edge. It was an example of the lightweight mirrors that could make it possible to launch a space telescope on a rocket. And the 50-inch remote telescope was steered from room 170 at the observatory's headquarters on the campus here across the street. Steering directions were entered into a Packard Bell 250 with punched paper tape and sent over the plain copper phone lines of the mid-1960s to the telescope. And this picture is Russell Knighty. He was the systems manager who helped build the rocket astronomy program and the remotely operated telescope program. Knighty traveled with Dr. Meinel for meetings with space and military agencies. So remember that construction photo with the board members everywhere. Here's that 36-inch telescope, all built in 1960 when the observatory was dedicated. It was the first major scientific telescope on Kitt Peak. And this is when Meinel resigned from being director of the observatory and was moved sideways to administer the space division around June of the year. He had overspent the observatory's budget, which risked the observatory's relationship with the National Science Foundation. And the job he was given, associate director of the space division, was a way for the bosses at Aura to keep him around while preserving their reputation with the NSF. His value outside of general administration was so obvious. Joseph W. Chamberlain was hired in 1962 when Meinel left to work across the street at the University of Arizona. Chamberlain was an astronomer and a physicist, known for research in the different causes for Earth's atmosphere to glow, from auroras to chemical reactions. He studied how planets slowly lose their air to space. And here is where the plot turns. Chamberlain would only take on the job of restructuring and running the space division if he could deprioritize the big space telescope and create a sounding rocket program. Sounding rockets were more practical and affordable and matched right up with what Chamberlain liked to study. The workhorse of the new Kitt Space Division rocket program was going to be the Araby. The Araby was a sounding rocket, a rocket designed for science. It was a hybrid that came from two military missile projects, one that gave the Araby its first stage and one that gave it its second stage. The first of those two missile projects was the Navy's Bumblebee program, where the solid fuel booster came from. This was originally built for supersonic surface-to-air ramjet missiles that were a response during World War II to attacks on ships by kamikazes. The booster gave a massive initial thrust to pop the rocket upward while it roared for about 2.5 seconds before the next stage took over. The booster in this photo was a larger, upgraded booster with more than twice the power of the original. It boosted for 3.4 seconds. And with more boost, Kitt had to make more rugged instruments, which you'll hear about. The main rocket body, or the upper sustainer stage, came from the liquid-fueled WAC Corporal, a ballistic rocket. WAC, or WAC, stood for Without Attitude Control. It was ballistic, which gave it fewer parts and made it mechanically simple, more reliable. This stage was the main engine that pushed the payload to the upper atmosphere. The Araby used a propellant that combined aniline and inhibited red fuming nitric acid, the oxidizer. These two chemicals ignite right when they contact each other, which is another way they kept the mechanics of the rocket simple. They didn't need spark plugs, and this chemistry is called hypergolic. They added hydrofluoric acid to the nitric acid, which chemically created a coat of aluminum fluoride inside the aluminum fuel tanks to keep the acid from eating through the rocket body. That's why we call them rocket scientists. Before launch, the rocket was assembled piece by piece onto an erector boom. And the erector boom let the rocket be hoisted vertically so it could be installed in the launch tower. And here we're looking down from above the rocket inside the launch tower. The launch tower could be tilted to compensate for winds. They wanted to make sure the rocket landed inside the missile range. Kitt civilian rocket astronomy program was launching its rockets from the high security White Sands missile range in New Mexico. And the Araby was a family of rockets. It had a long history with upgrades and variations. The Kitt rocket program mostly used the Araby 150 and Araby 170. And this rocket here would launch instruments that measured the ultraviolet spectrum of Jupiter 18 times during its flight, reaching 105 miles and using a 14-inch Cassegrain telescope and a photoelectric spectrometer. And they were helpful with those labels. This rocket is being made ready for a stellar spectrophotometry mission using a 12-inch telescope and a photoelectric grating spectrometer. When it launched on October 26, 1968, it was the very first all-up or fully operational flight of an Araby 170 rocket. When it flew, it reached a peak altitude of 152 miles. And this image begins to instruct us about how important duct tape is to rocket astronomers. A normal Kitt peak payload with telescopes, tracking, sensors, telemetry, radios, and recovery gear weighed around 175 pounds. And that solid fuel booster provided the initial high thrust launch that lasted about 2.5 seconds. Then the rocket transitioned to the liquid fuel sustainer that gave it a smooth, vibration-free ride after that. They could set the throttle control to park it at just the right altitude where they wanted to put their instruments. This launch on June 12, 1969, was to measure the ultraviolet spectrum of Mars using a 14-inch diameter Cassegrain telescope and a photoelectric spectrometer. After those 2.5 seconds of the hard boosting, the first stage would separate from the sustainer thanks to aerodynamic drag. It wasn't even mechanically attached. It just pushed up against the sustainer stage until the fuel was used up, and then gravity just let it fall out of the back of the rocket to the ground. That's a perfectly natural picture of a perfectly natural rocket launch. This launch in April 1970 used a Kitt Peak-built crystal spectrometer to capture the atomic fingerprints of sulfur being stripped from a star as it was eaten by a neutron star. Its ripped away gas was spiraling into a whirlpool where gravity crushed it, generating millions of degrees. The energy created a fog of loose electrons so dense it blurred the sulfur signal, showing the accretion disk was converting raw gravity into X-rays. When the Araby blasted off, its fins caused it to spin, giving it a gyroscopic effect that kept it flying straight. The flights reached their highest altitudes or apogees between 120 and 150 miles, 190, 240 kilometers. And when the rocket cleared the atmosphere and its fuel was spent, the spin from its tail fins would prevent or mess up astronomical observations if it wasn't stopped. Rockets would eject weights attached to cables from its side. I'm going to be dumb for a minute. So the rocket's spinning, and suddenly it's out of fuel and in outer space. It blasts weights on cables sideways, just like that, right out of the middle, and it stops the spin almost immediately. Then an attitude control system, or ACS, would fire small jets of cold gas to stop the rocket's rotation entirely. When the spinning stopped, the attitude control system took over to aim the rocket's instruments. These controls could aim the payload at targets with an accuracy of 1 minute of arc or better. Kitt Peak engineers made this possible. In a few ways, they used air jets to stop a rocket's wobbling or precession. It didn't just spin in a circle like this. It would also pick up a little wobble that they had to correct. By staring at guide stars with photoelectric guide telescopes and gyroscopes, they could keep an instrument glued to their target. They used cold gas thrusters to keep cameras lined up, and specialized pointing systems helped specific instruments hold their targets. To allow the telescopes to actually see space, the rocket's protective nose cone had to be jettisoned. A specially designed split cone was typically ejected by internal springs about 80 seconds after liftoff, clearing the way for the instruments. In this image, we see ports opening that expose the instruments in space. The rocket only spent from 5 to 6.5 minutes of time observing. During this window, automatic instruments made their measurements. The rocket launch in January of 1973 carried instruments for X-ray spectroscopy of a quasar, a spiral galaxy with a supermassive black hole at its center, and a point source of X-rays in the Virgo constellation. This was the second to last rocket program launch here. As gravity pulled the rocket back to Earth, the scientific payload section was physically severed from the heavy rocket body. This separation happened around 300 to 370 seconds after launch during the descent and prevented the instruments from getting damaged during re-entry by being attached to the heavy rocket body. When the instrument package got to a lower altitude, a pressure-sensitive mechanism triggered an explosive cord that deployed a parachute. The parachute lowered the payload to the desert softly at about 10 meters per second, which let the instruments and film get recovered and flown again. So why were we up there? During the rocket program period, there were a few reasons sounding rockets were needed. A big one was the view. Instruments were above all the turbulence in the atmosphere, above the Rayleigh scattered light, where they could see faint things and weren't hanging underneath a giant high altitude balloon that blocked their view. The Earth's atmosphere blocks or obscures many wavelengths of light. Rockets carried instruments above this interference, so astronomers can observe ultraviolet, X-ray, and far infrared radiation from space. It gets their instruments above the glare of scattered sunlight in the lower atmosphere to measure faint phenomena like the daytime air glow and zodiacal light. The instruments being recovered here were sent up above the atmosphere to measure zodiacal light on September 15, 1964. An individual scientist and a small technical team could propose, build, and fly a sounding rocket experiment in about a year. They could do new science and take advantage of tech developments with their rockets. Satellite missions needed massive lead time of 4 years or more. They were far more technically complex. And since the instruments on a sounding rocket would parachute back to Earth, they could be used again, saving money and speeding up the turnaround of the next launch that used them. This is an instrument from a flight in December of 1967 that carried a 14-inch telescope and a photometer that were used again in May 1968. The field of infrared astronomy was emerging and required telescopes and sensors to be supercooled, often with liquid helium. Coolants like this are volatile, and it's hard to store them for the long time needed for a satellite mission. But they were perfect for the short flights of sounding rockets. In this photo, the crew is preparing for a July 16, 1971 rocket flight that would carry a liquid helium-cooled telescope that would perform infrared photometry of the galactic center and other sources in wavelength bands ranging from 5 to 1,500 microns. And I told you that duct tape was important to rocket astronomers.
Yes. Yeah.
Oh, where are we going? You're going to find 3 rolls in here. There you go. And we can all agree that rocket scientists and rocket astronomers have plus-sized intellects. And that's why we don't worry for them when they're smoking a cigar by a rocket. So NASA was focusing their resources more and more on support for large space probes, humans in space, and the Apollo missions. Chamberlain said in a 1970 report, there are increasing signs of NASA leaving basic research for the more spectacular space ventures. Kitt had an independent rocket program that allowed scientists to fly instruments to pursue pure science or test unpopular ideas that didn't match up to larger federal missions. An example is when Kitt flew this rocket in December 1967 for Dr. R.C. Anderson when he couldn't get funding for his experiment from the National Science Foundation. The mission captured the ultraviolet spectrum of Venus. Then Anderson was a consultant for another launch in May 1968, which measured the ultraviolet spectrum of Jupiter. These flights were a big deal because they proved that the standard reflecting layer model used at the time for studying planetary atmospheres was not valid for Jupiter or Venus. The standard model would describe a planet's atmosphere as having a top clear layer and a lower reflective layer where light bounced off of cloud tops. Venus and Jupiter had more of a fog-like reflectivity. So this rocket launch changed planetary science by establishing a whole new model. And sounding rockets were a comparatively cheap way to do space research, which mattered when funding for major new satellite programs was hard to get. Satellites could cost millions of dollars, and they had to develop complex instruments that would last a long time in space. An audit of the Kitt rocket program in 1969 showed that the average cost of 21 rocket flights to be $417,000 per flight. This crew is preparing for a December 1969 launch. In the words of Chamberlain, the rockets were an interface between ground-based and orbital astronomy. They could see space as clearly as satellites could, but they were fast and cheap in comparison. They helped fill a gap during the time before satellites became more common. Here we see the preparation in May 1969 for a horizontal check of a rocket to launch in June. So the Kitt scientists were doing what the Space Division was intended to do, using emerging technology for astronomy. They were building, improving, and bulletproofing scientific instruments for each rocket launch and bringing home data that was feeding our understanding of Earth, the solar system, and the galaxy. This is the Airglow Lab. Early in its life, a tiny 2-room lab built in the 1960s at Kitt for studying the different reasons the Earth's atmosphere glows. When the rocket program began, the first bunch of launches were for these scientists, and one of the first things they discovered was a big deal. Clouds high in the atmosphere would absorb intense sunlight, but nobody knew where that energy went. It didn't bounce off as light. In April 1964, a rocket flight with 7 light meters figured out that this energy was absorbed by oxygen atoms, which they could see as a red glow. They learned that the oxygen crashes into nitrogen molecules, giving the nitrogen all this extra energy. This heats the nitrogen and told us how the upper atmosphere gets heated by the sun. The Airglow Lab has become the roll-off roof telescope operated by the Kitt Peak Visitor Center. And along the way, I'll leave this here for just a second. I gathered up a spreadsheet of all the data for each mission. There were over 30 missions that Kitt Peak flew rockets for. And this was interesting to me, how the missions broke out. You're here to read PowerPoint slides, right? Scientists originally thought X-rays from space passed through thin gas near their origin, which would produce a strong, clear signal for elements like sulfur. But when they used special crystal spectrometers on this flight in April 1970, they measured a weak line for sulfur in the spectra that showed the X-rays were actually having to push hard to get through a thick plasma of electrons that scattered the light. In 1971, a Kitt Peak rocket flight measured the atmosphere of Venus to test what kinds of hydrogen were in it. The Mariner 5 probe told them there was a lot of heavy hydrogen, deuterium, but the higher resolution spectrometer in the Kitt Peak rocket figured out from the ultraviolet spectrum of the hydrogen that it was almost all normal hydrogen, and this helped them understand how quickly the density of Venus's atmosphere changes with altitude. And ultraviolet spectra of carbon dioxide showed them that the cloud particles on Venus were completely mixed with the gas of the atmosphere like a fog. On June 4, 1969, the crew was doing a vertical check for a flight that would measure the ultraviolet spectrum of Mars while Earth was between Mars and the sun. The lead investigator, Lyle Broadfoot, and Lloyd Wallace wrote a paper about discovering that the planet had a generally flat reflectivity, which was different than expectations. And this February 16, 1968 flight measured the ultraviolet light of 20 different stars in the Orion region. This data confirmed theoretical models of how hot stars behave, which had been debated. This was a stellar spectrophotometry experiment. In 1970, after 21 launches, they gathered statistics about the success rate of Kitt Peak rocket missions and learned their own success rate was better than every other rocket program. They had a 71% success rate, while unofficial statistics showed NASA at 69%, the Naval Research Laboratory at under 70%, and the Air Force at under 50%. The whole program earned praise from the scientists who flew instruments with it. Dr. Donald C. Morton, a visiting investigator from the Princeton University Observatory, pointed out that the program's existence elevated the aerospace field, saying that the friendly competition between NASA and the Kitt Peak encourages both groups to improve the reliability of their flights. But some rockets still had sick days. This flight was launched on March 8, 1966 for Dr. Morton. It was meant to photograph the ultraviolet spectra of stars in the Zeta Persei region using two objective grating spectrographs. But a thruster on the rocket's attitude control system wouldn't fire, so the rocket tumbled in space and the instruments parachuted back to the ground okay. This rocket, launched on January 18, 1966, was a second mission to gather spectra of stars in the Orion region using a 12-inch telescope, and there was a train wreck of mechanical failures. At 48 seconds after launch, the rocket's sustainer engine had to be shut down because of a rupture in the chamber pressure monitor line, and with the engine gone, it all tumbled. A helium leak killed the attitude control system caused by a badly tightened nut on a pneumatic line. This one, launched on December 16, 1966, was a repeat mission for stellar spectrophotometry. The rocket's second stage suffered a high-frequency transverse instability that caused its inner liner to be ejected. And here's some of what was left of it after the rocket disintegrated at about 200 feet. The Kitt rocket program was a crucial stepping stone in space exploration. It provided individual scientists with a fast, flexible, and relatively inexpensive way to test new technologies and gather data from space for years before more complex satellite launches became common. So we've had almost 10 years of flying rockets to space, but now we're up to 1970, and money is becoming tight at the observatory, where they were level funding and prioritizing the completion of a new giant 4-meter telescope. Aura directed Kitt to lower the priority of its rocket program, which funding had already shrunk to 2 or 3 flights per year by 1969. The rocket program was forced to make a plan to use up all of their rockets and attitude control system hardware by 1975, flying up to 3 flights per year for only 3 more years. Funding from the NSF was getting harder to secure, and politically, ground-based astronomers didn't feel the rocket program was a good use of it. Kitt director Leo Goldberg said in a 1983 interview, "I had to cancel the rocket program because the budget was really being slashed, and that program was meeting the needs of maybe 3 experimenters a year at a cost of $500,000 or more." When a sounding rocket was sent into space, it flew up on a parabolic orbit, up and down again. It went up into the vacuum of space, but it did not enter an orbit. The rockets would go above the Kármán line, where you have to be a rocket to fly because there's not enough air for an airplane 62 miles up. You're in space, but the rockets would swoop right back down again. This gave Kitt a chance to point out that these rockets weren't officially, by definition, a spacecraft, which was the domain of NASA now. The National Science Foundation wasn't allowed to fund space exploration, which had become NASA's job. This rocket lifted the 1968 Orion Stars mission. So even though the rocket lifted actual space instruments to actual space, Kitt could say that they were just putting telescopes, an extension of the observatory, at higher altitudes, and they weren't really being competition to NASA. The NSF used this idea in their arguments to fund the rocket program while they could. The rockets were needed for repeated or synoptic observation of the atmosphere, and the rockets were a platform or research tool, not a vehicle or spacecraft. This made the rocket payloads into the laboratory equipment of a ground-based program. But even after years of successfully using the argument that Kitt rockets were just lab equipment, not a national space program competing with NASA, the priorities of the Kitt administration narrowed, and the rocket program had to fall away. This is the rocket that carried Dr. Lyle Broadfoot's ultraviolet spectrometer to look at the atmosphere of Mars in 1969. Now we get to remember the very lasting triumphs of the rocket program. One of them is how the science team made instruments better and better for flying on rockets, smaller, tougher, more sensitive. And here at the University of Arizona, you might recognize Dr. Lyle Broadfoot at one of his Kitt Peak rockets. And here's Dr. Broadfoot in 1972 at NASA's Jet Propulsion Laboratory as the ultraviolet and spectrometer principal investigator for the Viking missions to Saturn and Jupiter. Because the pointing systems for space astronomy in this era just weren't good enough, the rocket program had to invent rocket stabilization and pointing systems. Rockets at first could point within 2 degrees of a target. And thanks to Kitt Peak's designs and the contractors who built them, rockets could get a pointing accuracy as fine as 1 arc minute by the time the program ended. This rocket was the one that observed the atmosphere of Venus in 1969. To manufacture these various rocket astronomy inventions, Kitt Peak worked with aerospace companies like Space General Corporation, Hughes Aircraft Company, and Aerojet General. The stabilization technology they created was adopted by the Naval Research Laboratory, the NRL, for its own solar X-ray flights. This photo is of the attitude control system pneumatics in an Araby 170. And here's recovering one of the Naval Research Laboratory instrument packages. Remember, the instruments came down on parachutes. They could be reused, and they were. This saved money. We're near the end here. It's no longer a mystery. Yes, rocket astronomers can give us fashion cues. And some clubhouses are just better than others. With all the information you heard tonight, you should know we've just touched the very surface of the history and science preserved in the Kitt Peak rocket program. Every flight had a logbook with reports, test results, telemetry, invoices, correspondence. A real rocket historian with some science acumen could do a very, very deep dive. And part of my effort has been to digitize these images. So far, there's about 600 high-resolution scans, and the number's growing. There's still boxes of images. Polaroids were taken constantly, and I haven't touched those yet. I have the pleasure of immersing in this story because the very last manager of the rocket program, Lloyd Vincent Wallace, preserved all of this. This collection is at the Norlab Library across the street and is now known as the Lloyd Vincent Wallace Rocket Program Papers. I'm continuing to index the contents and scan the documents and images. I work with librarian Sharon Hunt and graphics boss Pete Marenfeld. And by the end of the year, I think we'll have put this part of America's astronomy history back where it can be appreciated. Here's Dr. Lloyd Vincent Wallace. He was the principal experimenter for the rocket program when it started, and by 1972 was the acting associate director of the whole space division, which was now known as the Planetary Science Division. He was an investigator on 9 rocket launches and wrote or contributed to 135 scientific papers. When he passed in 2015, he was remembered as a genuine person with a very sharp wit. And I'll leave you with this picture of instruments that were sent up to measure the near-infrared day glow and solar X-rays in 1966. And if you learned anything tonight, it should be when you find yourself standing in the middle of the desert with a random rocket astronomer, you'll know what they're holding in their hands. Thank y'all.
Yeah, plenty of time for questions. And if any of our viewers on Zoom have any questions, please type it into the chat box on Zoom and we will read them out. Here, okay.
These rockets that you described have pretty impressive control systems. But those were all analog control systems. I didn't see anything that looked like computer hardware. I was using computer hardware in 1970s, so
I know there were cars, I can't say how to do this, I just don't know yet.
my question is more basic. So although it was called the Kitt rocket program, almost all of us happened at White Sands and administered through the Kitt Peak organization. Is that correct?
Yes, there were partners with military organizations like the Navy and the Army for access and for the logistics of the launches, of course. But it was Kitt Peak scientists developing, improving the instruments and the control systems. This is helium.
You have a question?
Okay, backing up to the selection of Kitt Peak from possible ones, was there any political considerations or is it no? Strictly, this was going to be the best viewing high altitude mountaintop that they could come up with.
The process I described for the site survey lasted a couple of years, and they actually ended up with two mountaintops that were identical in the quality of their scene and in their viability for a national observatory. One was in the Hualapai Mountains, and it happened to be about 3 hours from a big city. And Kitt Peak just won between the two because of its proximity to Tucson with an airport and a hospital and a university. And then, of course, the conversation with the Tohono O'odham, who are a very, very thoughtful culture, lasted a couple of years.
You have a question?
Yeah, a couple quick questions real quick. Okay, so I'm assuming you can really have mishaps or whatnot, but none of this stuff, I guess, burned up in the atmosphere. It just looks like going fast enough, correct? And the other question is, are you going to put this in a book? It looks like it'd be really cool history to have.
I love that. My expectation of myself is that this picture show will become a narrative that's illustrated with more detail. There's so much more to share, and I realize we got a little fine-grained with dates and observations, but just the fact that we had a rocket program of this scale was really special. And if you wonder where my interest comes from, over at the Norleth headquarters, the headquarters for Kitt Peak, the material you're seeing, these pictures I took of it, they've been essentially in boxes for 50 plus years. So learning that this existed in the first place was exciting enough, and then learning that it had pictures to go with it was pretty special. And in my exploration of the history of Kitt Peak, I'm working on histories of each of the telescopes as well for fun. I learned that in the 25th anniversary publication of the history of Kitt Peak, there was one sentence that said Kitt Peak started a rocket program. And there was a second sentence right after that that said, and then Kitt Peak ended the rocket program. And that was the tip, and maybe there was a story to tell. So here we are.
We have a question from Peter. who's watching on Zoom. He's just asking, just to confirm, no launch ever took place from Kitt Peak itself.
No, we never set the mountain on fire with 2.5 seconds of solid rocket booster from Kitt Peak.
Any other questions? Yes.
We kind of breezed by the role of the 50-inch telescope on Kitt Peak. Is it my understanding that was used simply to test this new lightweight mirror that had been designed?
It was a test bed of an infant technology that hadn't existed before, remotely controlling the telescope. And for all the years that they worked on it, they never got it just right, controlling the telescope as finely as they needed to remotely. With the equipment they were working with in the 60s, never quite worked right. And the leadership of Aura changed the telescope back to a manual telescope in the late 60s before the technology was mature. It was at the same time they were experimenting with the aluminum mirrors. They tried other metals too, but aluminum covered with nickel was the most promising. But the metal had issues with changing shape with heat changes. They never perfected that either. So the natural progression of all of this was to sort of to stall out while NASA picked up this multi-stakeholder, multi-million-dollar, multi-year space telescope project in a way that relieved Kitt Peak of the mass of that project. And the telescope that they built to be remotely operated, this is such a Bible, but it's fun for me. They built the dome with a shutter exactly as wide as the remotely operated telescope. So when they turned it into a manually operated telescope requiring a finding scope attached to the main telescope, grumpy astronomers had to move their dome back and forth.
You have a question up here?
Okay.
Well, I know this is way before they have neurosculpting in the workplace. My question is, people used to sculpt on airplanes all the time, on airplanes. So why would scientists be smoking if they know it's dangerous? Oxygen is.
I did my political best to ease us into seeing that, to witnessing that.
Any other questions? Oh, okay.
So as I understand it, the first launch of the program was in '66, and the final launch was what, 1975, or was that when the program ended?
Rockets were being launched from 1963 to 1970. They hoped the program would go longer, it didn't. But 63 was the first one.
I did notice, though, that all of the failures that you pointed out all happened in 1966. Was that a selection effect on your part, or
No.
was there a reason for that?
No, there were some that failed before they launched, but they figured it out. Like they dropped the screw and grabbed another one and forget they were supposed to solve the screw in half before they stuck it in and caused the short circuit, that kind of stuff. But one of the things I mentioned very quickly, and I didn't say in any detail, is they do horizontal checks, vertical checks. They do checks all the way through the process before they launch it. So they found some stuff like that before they launch.
All right. So once again, on behalf of the director of Stewart Observatory, I'd like to thank you all for patronizing our public lecture series this academic year of 2025-26. This is our last lecture of this academic year. We will start again probably either the Monday after Labor Day, depending on the phase of the moon. But you will see here on our website sometime this summer our schedule of lectures for the fall 2026 semester. The telescope is closed. Have a pleasant rest of the springtime, and let's thank Jim one more time.
Anybody have